In this video, I will be presenting our work titled NoC Symbiosis. In this talk, I will demonstrate the concept of NoC Symbiosis and how it will radically transform NoC design in computer architecture. This work was done by Daniel Petrisko, Chun Zhao, Scott Davidson, Paul Gao, myself, Dustin Richmond, and supervised by Michael Taylor. We are part of the Bespoke Silicon Group at the University of Washington. I'd like to start my talk by analyzing a simple model of a 2D mesh router, as shown on the left-hand side of this slide. The router exists within a bounding box and has ports for each of the 4 cardinal directions: north, south, east, and west. Abstractly, routing wires must travel across the bounding box in the horizontal and vertical direction to connect the ports. The router itself is parameterized by the link width, which is the number of ports in each direction. Conventional wisdom states that as we increase the link width, the router area must grow quadratically. So if we double the link width from 4 to 8, the router area will quadruple in a quadratic relationship. In NoC Symbiosis, we demonstrate that conventional wisdom is flawed, because conventional wisdom oversimplifies the characteristics of routers. In fact, if we look more closely, we can see that as the link width increases, it is the wiring area that scales quadratically, and the cell area actually only scales linearly. To demonstrate this concept, we have annotated the previous figure with switches, where the horizontal and vertical wires intersect. The number of switches is an accurate approximation of the cell area of a router. And we can see that if we increase the link width from 4 to 8, as we did in the previous example, the wiring area quadruples in a quadratic relationship, while the number of switches, or the cell area, only doubles in a linear relationship. This divergence of wiring and cell area is detrimental for conventional design practices, where the design logic and NoC logic are considered independently. A conventional design flow is typically a 3-step process, as shown. First, the design node is placed within a bounding box. This could be an accelerator or processor or other application logic. Second, the router is designed separately to meet bandwidth, latency, and independent area constraints. Finally, the 2 parts are integrated into a single tile floor plan, which is then replicated across a chip to create an architecture. This divergence of wire and logic resources is detrimental to architecture design because it forces designers to choose between the lesser of 2 evils. Designers either choose to balance the router cell and wiring area to get high cell area utilization, which produces low bandwidth routers, or designers choose large network links, which yields poor cell area utilization, but high bandwidth. The key point of NoC Symbiosis is that we can recapture this underutilized area, and that doing so would revolutionize network-on-chip design, because it would produce high bandwidth NoCs with linear area cost. The key idea behind this revolutionary NoC Symbiosis concept comes from understanding how the interconnect is used by different parts of the design. This slide depicts a relatively modern process stack, which we have split into 3 regions. At the top, we have the power grid, which has large, relatively sparse wires. Below that, we have the long-distance routing wires, which are used to move signals a long distance across a chip. Below that, we have the logic area and local routing, which is used to connect transistors. Now, if we focus on the lower 2 layers, and we study how the node and NoC utilize these process layers, we can see how the concept of NoC Symbiosis arises. In particular, if we look at the node, we can see how the node has relatively low utilization of long-distance routing wires and relatively high utilization of logic area and local routing, because node and NoC designs typically implement processors and accelerators, which are compute intensive and have connections between nearest neighbor transistors. In contrast, the NoC has complementary usage of these layers. The NoC has high utilization of long-distance routing wires, but relatively low utilization of logic area and local routing, for the reasons we demonstrated previously. Now, the key idea is that these two different pieces use complementary layers, so that if we combine the designs, if we combine the floor plans into a single symbiotic floor plan, we can get high utilization of the long-distance routing wires and high utilization of the logic area and local routing. This is the key idea behind NoC symbiosis, is that by combining the node and the NoC into a single symbiotic floor plan, the node will absorb excess logic area from the router, and the router will absorb excess routing area from the node. This design practice yields two extremely beneficial options. Designers can choose between an order of magnitude improvement in bandwidth for a slight area increase, or designers can choose constant bandwidth for a smaller combined area. We will demonstrate this choice in our results. But first, I'm going to briefly recap how we discovered NoC symbiosis. We first discovered NoC symbiosis with Black Parrot. For those of you who are unfamiliar with Black Parrot is an open source, tiled, Linux-capable RISC-V coherent multi-core processor. It has NoCs for coherence, memory, and I/O, as shown on the right-hand side of this slide. Black Parrot is designed as a base class for the next generation of accelerator-based SoCs. For example, Black Parrot can be used as the host processor for machine learning accelerators to reduce total system power and latency. If you're interested in Black Parrot, we encourage you to join us. You can fork, clone, and contribute to the project through the GitHub link below. The discovery of NoC symbiosis occurred during our first attempt to tape out The discovery of NoC symbiosis occurred when we first taped out Black Parrot. Now, if you indulge me for a moment, there's a short story behind the discovery of NoC symbiosis, and it is quite humorous. It involves our first attempt to tape out Black Parrot. During the first year of the Black Parrot project, we decided to tape out our RTL. At the time, Black Parrot had 5 on-chip networks. And in our initial design meetings, we sat down and tried to figure out how wide each network should be. We had been simulating the design with single FLIT packet networks. Since we were simulating this, we decided to try and tape it out. We believed this was a ridiculous idea, but we didn't have any evidence that said otherwise. The design had 8 to 10 times more bandwidth and wires than similar sized designs. The router used all of the available wiring tracks. We had designed many chips in our group, but this was an order of magnitude above all of those designs in complexity and bandwidth. We then followed a conventional design process. We designed the processor and node as we described previously. We put each of them within separate footprints and planned to combine them late in the design process. Even better, we distributed these floor plans as a design challenge to the undergraduates in our group. As you can probably tell, this was a disaster. When implementing the router, the tools never finished. And when they did finish, they had DRC errors. When we ignored the floor plan and just implemented the router, the cell area was vastly underutilized to the tune of 10 to 20%. After spending weeks, we were ready to rip up our progress and start again from scratch. However, we were saved by the discovery of NoC Symbiosis. During a design meeting one day, one of the postdocs in our group, not myself unfortunately, mentioned casually that they had placed and routed the entire processor, not just the router, and it had finished with no problem. No DRCs, great utilization, met timing, and fit in the area of the combined floor plan. This was a stunning result. And if we look back, this was the key moment when we discovered NoC Symbiosis. Once we realized what had occurred and that we had happened on NoC Symbiosis, we sat down and came up with 4 important questions that examined the fundamental science behind NoC Symbiosis. First, at what link widths does NoC Symbiosis offer benefits? With Black Parrot, we had demonstrated a link width of 5,000 wires demonstrated benefits, but this was a ridiculous design point. Could we achieve the same revolutionary benefits at a smaller design point? Second, how effective are CAD tools at automatically exploiting NoC Symbiosis? Historically, CAD tools have done a poor job of distributing logic through an underutilized area. Had this changed? Third, what are the quantitative benefits of NoC Symbiosis? Could we develop a rule of thumb that future architects can use to design their systems? Finally, to what extent did prior chip designs leverage NoC Symbiosis? Is this a concept that has been exploited since the beginning of time, or did we stumble across this new and unexplored region? To answer these questions, we developed a series of experiments. The network configuration used a 2-dimensional mesh router, as we demonstrated in the introduction, with dimension-ordered routing, as we have used in many of our designs. The router was also configured to use wormhole links, so that our results are not limited to single-flit, single-cycle packets. In these experiments, we varied 2 parameters. First, we varied the link width, as we showed in the introduction. And second, we varied the pitch and process constraints. Specifically, we varied them between 2 different configurations. First, double layer double track, or DLDT, which approximates modern technology and uses multiple layers to densely packed pins. And SLDT, or single layer double track, which approximates older routing limited technology nodes. In this talk, we only demonstrate our DLDT results, but we encourage you to read our paper where our SLDT results are shown. SLDT actually improves NoC Symbiosis. In these experiments, we took 4 measurements. First, we measured the total router area. Second, we measured the standard cell area. This was the area consumed by only the standard cells of the design. In contrast, the total router area, which considers the bounding box that surrounds the wiring. Third, we measured the utilization, which is the standard cell area divided by the router area. Finally, we measured the maximum bandwidth. This is a function of the link width. All data in this talk is using full synthesis and automated place and route of actual NoC designs in 12 nanometers. Specifically, we use the source code on GitHub that we use for designs in Black Parrot and Hammerblade, shown at the link below. When does NoC Symbiosis offer benefits? To demonstrate this, we collected 2 graphs. First, on the left, we have the graph of router area versus link width. On the x-axis, we have the network link width in wires, as we varied it from 16 to 2048. On the y-axis, we have the router area in square microns. As the network link width increases, so too does the router area, and specifically, the router area increases quadratically as the network link width increases. This is consistent with conventional wisdom. On the right, we have the graph of area utilization versus link width. On the x-axis, we have the network link width, again in wires, as we varied it from 16 to 2048. On the y-axis, we have the router area utilization from 0 to 100%. This is the standard cell area divided by the total router area. As you can see, initially, the router area utilization is constant up until a network link width of 400 wires. At this point, the utilization begins to drop, and it drops quickly. It drops from 80% and eventually stabilizes around 20%. So when does NoC symbiosis offer benefits? If we look carefully at these graphs, we can see when NoC symbiosis begins to occur, when the router becomes underutilized. This design point occurs around a network link width of 320 wires. We call this the symbiosis threshold. To the left of this region, we call the conventional region, where independent place and route of individual design pieces will produce a good result, though it does not produce a maximum bandwidth result. To get this, one must enter the symbiotic region to the right of the symbiotic threshold. At this point, it is beneficial to place and route the two pieces of design logic to achieve maximum bandwidth and area utilization. On to the second question. How effective are CAD tools at automatically exploiting NoC symbiosis? Again, we demonstrate this with two graphs. On the left, we have the graph of recoverable area versus link width. On the x-axis, we have the network link width and wires, after the symbiotic threshold and up to 1024 wires. On the y-axis, we have the area in square microns. On this graph, we show two lines. First, in black, is the unused router area. This is the total router area minus the standard cell area. Effectively, the area that wasn't used by the router. The dotted line we call the attained area. In this experiment, we inserted additional logic and measured how much we were able to insert. As you can see, as the network link width increases, the unused router area increases. And so too does the attained area. On the right, we have the graph of recoverable utilization versus link width. This is effectively the dotted line divided by the black line. On the x-axis, we have the network link width in wires. And on the y-axis, we have the unused area utilization. As I said, the dotted line divided by the black line. As you can see, initially, the utilization starts at 40%, but quickly increases to 60% and eventually to 80%. So we can conclude, how effective are CAD tools at automatically exploiting NoC symbiosis? And the answer is quite effective. We can achieve 80% utilization of the unused area. Third, what are the quantitative benefits of NoC symbiosis? To demonstrate this, we show a graph of total router area and standard cell area versus bandwidth. On the x-axis, we have the maximum bandwidth in terabits per second. On the y-axis, we have the area in square microns. This graph demonstrates two lines. First, in solid black, is the total router area. As you can see, the total router area increases quadratically as the maximum bandwidth increases. Second, on a dashed line, is the standard cell area of the router. As you can see, the standard cell area increases linearly as the maximum bandwidth increases. Now these growth trends, or the difference in growth trends, exposes a bandwidth area trade-off. And if we annotate this graph with the conventional and symbiotic region, and if we pick a design point in the symbiotic region, we can actually achieve area reductions by recovering the unused area in the router. In this example, if we choose a design point around 40 terabits per second, we can achieve 3.3x less area. And if we choose a design point around 100 terabits per second, we can achieve 5.9x less area. This brings us to the interesting conclusion. The more bandwidth you need, the more area you can save. On to the final question. Have prior works leveraged NoC symbiosis? To demonstrate this, we surveyed a variety of similar prior works that used two-dimensional meshes and tiled architectures, and scraped results from those papers. In addition to these results, we used three different design points from Black Parrot. First, V0, which I described initially. It has large networks and incredible bandwidth, and is deep in the symbiotic region with 5,000 wires per link. Second is V1, which uses reduced width and dimensionality to bring the design back into a conventional region. Finally, V2, which has realistic bandwidth provision for the processors. Now, if we plot these points on the graph of router area utilization versus link width, we can see that few prior works are symbiotic. Only Black Parrot and one prior work exist in the symbiotic region, and only Black Parrot v0 has actually explored the deep symbiotic region. If we compare between designs, normalizing for area, we can see that with Black Parrot v0, we were able to achieve an order of magnitude improvement in bandwidth. If we analyze this graph further, we can see that few architectures have actually explored the symbiotic region. So we encourage architects to go forth and explore this region. Each architecture has a certain amount of bandwidth that it can usefully leverage, and NoC Symbiosis can get you closer to that optimal point. Symbiosis can lead to revolutionary new architectures. We are already exploring this region with Black Parrot version 2. More recently, we have explored the symbiotic region with Hammerblade and Roosh Networks, our partner paper at this conference. To conclude, what are some of the takeaways of NoC Symbiosis? First, router area is underutilized, particularly as the network link width increases. This happens because the standard cell area does not increase quadratically, while the total router area does. This unused area can actually be recovered with NoC Symbiosis, and this gives us order of magnitude bandwidth benefits for little or no area cost. Third, NoC Symbiosis offers a huge benefit in both bandwidth and area. For example, we demonstrated that we can achieve an 8 to 10x bandwidth improvement for a small area increase. We also demonstrated that designers can achieve smaller routers for the same bandwidth. Third, these benefits increase as the network link width increases. Finally, we also found that few prior designs use NoC Symbiosis. However, given the revolutionary nature of NoC Symbiosis and the massive area and bandwidth benefits that can be achieved, this number should increase, and it should increase quickly. Before I conclude this presentation, I would like to make a few acknowledgments. This material is based on research sponsored by the Air Force Research Laboratory and Defense Advanced Research Projects Agency under the grant numbers shown below. This work is also partially supported by an NSF SATC award and the ADA Center. With that, I would like to conclude my presentation and thank you for your time.